Hi. So I am going to talk about plants which are very, very good at marrying mechanical information to its morphogenesis and pattern formation. A picture is worth 1,000 words, and you can see plants, funky plants looking like this in coastal lines of UK for sure, somewhere very windy, where there's a monodirectional wind and open field quite often. This tree was captured in a windless day in Seven Sisters area of southern UK. So yeah, they're very good at sensing the mechanical demands imposed upon them, either from externally, like by touching wind, or from within their own body, from intrinsic mechanical stress. And they basically adjust their morphology and anatomy to deal with that. So this is a laborat plant, Arabidopsis, basically a brassicaceae weed, easy to grow, small genome. Yeah. So they are growing normally in here, and but you can turn them into little bonsai plants just by touching them every day, basically. They become stiffer, they become dwarf, they become ready to take on any further sort of mechanical agitation. So in my young lab in Edinburgh, we want to understand how they do this through active mechanosensing and response, especially a response involving developmental decision making. So before going too further, plants are sort of nice systems for mechanical studies for another reasons. It's relatively easy to apparently model or think about their structures mechanically because they're like balloons or shell. Their cell, which is relatively soft, is surrounded by a rigid cell wall. So the shapes, the control of the shape depends on this structurally much stiffer element outside of the cell, the extracellular matrix. And so basically plant cell is like a pressure bomb, pressure vessel. And while it's easier probably to model it mechanically, but if you think about as a plant cell, it's actually tricky to grow if you have such a high internal pressure. It could be as much as 10 atm. So imagine the automobile tire, to glowing automobile tire. How do you, grow, change the shape without exploding? And the same problem apply to the plant as an entire sort of organism, organ at the tissue level, because there's a lot of sort of tagger pressure, the internal pressure of the cell, together comprise an internal pressure of the tissue. And that's borne by basically the outermost cell layer, the skin cell layer, especially the outermost cell wall, which tended to be about 10 times thicker than other cell walls anywhere else. And this skin layer seems to have a lot of important molecular factors regulating the shapes of plants, plant organs, tissues as well. So again, plants are like balloons. And that's how we try to think of it to make our life easier. Again, but growth shape control is tricky. So their regulation of morphogenesis seems to, it makes sense. They seems to utilize mechanical information, mechanical signal to disperse this structural instability as much as possible. For example, in regulating direction of cell expansion, what they do is they utilize the information of a mechanical stress, the maximal sort of direction of a mechanical stress, and then realign the structural element of the cell wall, the cellulose, parallel to the direction so that the cells can grow more easily perpendicular to that direction. So they are dispersing the accumulation of a mechanical pressure at one point. So this has been beautifully described 2 days ago by those in the audience. So hopefully it's ringing a bell in your mind. And so this is basically a feedback loop to make the structure more structurally robust, so structurally more stable. So they use the shape information to orient the structural element, and then that induces anisotropic growth, so that the shape is stable as a structure, and it goes back and forth. Also, regulation of growth, to how to induce growth and how to induce growth. Well, that seems to involve sort of a sophisticated mechanisms, which is a little bit counterintuitive. So I want to tell you my postdoc work, which is a little bit old, but I wanted to share with you because I feel like you can tell me like new insights about how to interpret the results. So we wanted to see at the tissue level, comparing the high growth sort of area of a tissue, which undergoes very fast growth, versus the area of a tissue that doesn't go, that's very slow growing, and then compare if we can explain the difference by differential material properties of this outermost cell layer. So I use the word deformability to avoid the issues of a lot of nomenclature, terminologies. But by deformability, I mean the entire sort of a stress-strain curve. How much force you apply and how much deformation you can observe for the tissue level material properties. And traditionally, it's been thought, because growth is an irreversible deformation, induction of growth is all about making the cell wall material reach this phase, the plastic irreversible deformation phase. So make the cell wall softer to make so that it reaches the plastic phase easier. What we found was actually opposite. So the system we used is the shoot apex, a tip of the shoot where new organs and stems are being generated. Here is the mother of all the stem cells. Well, that's a long way to say it, but this tiny structure, about 100 micron, it makes basically all the shoot tissues, post-embryonic shoot tissue in plants. So there's a meristem. So this is called a meristem, and it harbors a stem cell population in the right middle, which does not grow that much at all. That right next to it, though, that's where the new organs like leaves or flowers are initiated, as well as the stem tissue, and they are quite fast growing. And it's quite starkly different. If you follow the growth dynamics, you can easily identify the different domains. So this is a 11-hour sort of time lapse growth rate monitoring, and basically this center domain does not expand as much. Well, they have less than half of expansion rate compared to the tissue right next to it. So that's the central region, the stem cell harboring region, and that's the peripheral region. And we wanted to gain insights into the material properties of those two different domains. And to do that, we basically shrunk the balloon. We got rid of the turgor pressure, the internal pressure, with a plasmolysis or hyperosmotic expansion. We just basically treated them like balloon and monitored the differential deformation that we observed. So basically, we got rid of, so we tried to get the difference state, of the tissue. And what we saw had a sort of, was a differential material behaviors. So for the shrinkage, due to the loss of internal pressure, was pretty much uniform everywhere within the meristem. But once we tried to, that's shrinkage, it was a 10% loss. But once we tried to expand it with a treatment with a pure water, the meristematic, the central stem cell lesions basically did not expand at all.
I have one question.
Yes.
Do these cells, are these cells devoid of a rigid cell wall?
It has. It's a living tissue, living meristem.
But if you shrink it, how can it shrink? We
Oh,
need to crumple then the cell wall?
We treated them with a super hyperosmotic solution, so that all the water came out.
Yeah.
And the plants are okay with it. As long as it's a relatively short period, you can go back and forth, back and forth.
So you see how the cells shrink within their cage, basically, or
yes,
the
it's
whole
within
structure?
the cage. It's actually pretty spectacular. You can see the cage like that, and then it shrinks slowly like that. And when they detach from the cell wall, then the internal pressure is just zero. Yeah. So that's what we did. And so using this information, we try to understand what kind of materials consist of different domains, and obviously it looks different. To get to that, though, that's assumption already. We are assuming that's differential material properties, but there are a couple of different ways of understanding these results. Yeah, and we try to sort of eliminate a couple of possibilities, other possibilities. One of them was just pure geometry, because it has such a complex 3D geometry, this structure. So maybe even if it's made of the same material, it could result in differential, deformabilities. So to do that, we did a FEM model, used the real geometry of the structure, and basically induced the internal pressure change, which is consistent with the experiment. That's the result. So that's a surface curvature with the hyperosmotic, so the expansion of the increase in the internal pressure causing the expansion, and those are the predictions. And it did not really match the experimental results, so probably the geometry is not. We also logically excluded the possibility of differential internal pressure as well, and well, we did not completely eliminate all other possibilities we could think of, but we felt like, okay, so there is a pretty good possibility it's due to differential material properties. Why don't we identify what kind of materials they are by, again, doing FEM modeling, simple one. We assume the meristem as a sort of half of the sphere, composed of two domains, and one, the central domain and peripheral, and then basically selected for a type of nonlinear stress-strain curve that fits the observation with the changes in internal pressure we introduced. And I'm sorry, I'm a biologist, and I should have equations and so forth, but my computer scientist collaborators claim, well, I shouldn't say that, but I don't quite understand how, but they got one equation for each domain, apparently, and that was for central domain. So it's very similar material. The only difference is the center was composed of relatively softer overall tissue compared to the fast-growing peripheral zone. So it's actually tissues are getting more stiffer overall to induce growth. The difference is the peripheral zone was easy to expand and shrink. They were in the elastic domain at the normal internal pressure range, whereas the central zone, the stem cell containing zone, was at the strain stiffening phase. So it was hard to expand but easy to shrink. Yes. Yeah.
Are you talking about the surface or the volume?
It's surface.
So
it's only the surface.
In the interior?
Interior, we basically make it as a sort of we are modeling as if they are a balloon, basically. They are focusing, we are assuming the outermost layer, the outermost cell wall determines the shape.
I mean, the center of the organ.
Yes, yes, so this area, so this meristem area so this is the center where it doesn't grow as much, and then that's the peripheral that grows a lot.
I'm asking, are you considering the entire 3D organ?
Yes.
As including a center and a periphery?
Yes.
Or you're just considering the center and periphery of the surface of the organ?
This-
Yes. So I can see the surface, but I can't see the interior.
Yes.
Right. So are you dividing it up conceptually into center and periphery only on the surface, or is there a center and periphery that
Only
goes
on the surface. Yes. Because
My understanding is the yellow part is their central part, I would assume.
yes,
It's
that
still on the
yellow
surface.
one.
And that's what they are monitoring.
But so you don't have any, you're not tracking anything on the interior?
No, no, not at this point. Of course,
And not
that's
thinking-
something
and
good
not
to
considering
do.
anything else.
But it was first quite easy to monitor the surface, cell deformability. So that's where we started. But also we are basing our assumption on those like experimental and conceptual sort of idea that plant tissues are like balloon. So the outermost layer defines the changes in the shape and growth and so on. Yes.
Yeah, one question. I'm a physicist, so I always wonder about numbers and units.
Yes.
At what order of magnitude strain do you see the strain stiffening? Is it 1% or 100?
So with this method, the elastic range of the deformation we saw for the peripheral zone it's the max like 25%, but more or less I think it was like about 10%, 50% was. And then the expansion too for the peripheral zone was similar. It was similar degree, yeah. But in the center, we basically didn't see much expansion at all. Maybe there is a variability. It's a noisy data. Yes, but yeah. Yes, and so what was surprising was, that it seems like a growth regulation is happening at least in this very young cell domains of shooter apex, that through the making the material stiffer overall, surprising. But also it seems like that there's a lot of elastic deformation, expansion happening in the normal state. And perhaps this elastic deformability corresponds to growth capability. In a way, first they deform, grow by elastic deformation, and then the cell will remodel to fix it, to make it irreversible, rather than as we used to think, well, this is still valid ideas for many different other tissues, that it's about bringing the tissue to this stage so that the molecular bonds break to, grow. So yes, this kind of mechanism actually is a safer mechanism, to not to sort of rupture due to the making the cell wall vulnerable during the growth. So that might make sense considering how much pressure the plant cells tend to have normally. And yes, I'd like to sort of switch gears a little bit to how morphogens or morphogenically active directing factors, molecular factors, can be sensitive to mechanical cues. And when you talk about development of plants, you cannot ignore this phytohormone hormone, often growth-inducing factor called auxin. Well, they are important from embryogenesis to organ initiation to organ expansion to any sort of localized decision making to induce new organs in shoots and roots, but also to induce localized growth as well. For example, if you knock the plants off to the sideways, they have this way to reorient their stem to fix it, their axis of growth perpendicular to against the gravity, which is called the gravitropism. That kind of fixing of a growth axis involves localized growth induced at the point of sort of bending. And again, like auxin is involved in events like that in general. So that this auxin, some people consider it's some kind of electricity-like thing, or it's almost like money. It goes around throughout the plants all the time, and then they get somehow the cues, points, make them accumulate at very locally at one point, and that switches on and off some important developmental decision making or induces growth. And this directional active flows of auxin is mediated by the efflux carriers, family of efflux carriers, called PIN, and they are usually, do I have it? No. Localized to one side of the cell. It's very polarly localized, and that brings about this directionality to this flow. And so when you talk to plant biologists about polarity, it's often about PIN polarity. It's so important. So plant development is very, some very important events in plant development is sensitive to mechanical cues. For example, if you bend the root, the primary root, you can induce the new lateral root, new organogenesis just at the convex side of the bend, and that's pretty dramatic event, I would say. And that involves depolarization of PIN protein at the particular cell, couple of cells, 1 to 2 cells maybe. And then that creates new maxima of auxin. And then this maxima of auxin induces a new root development by inducing root apical meristem activities.
One question. Do
Yes.
I have to imagine this PIN protein like a pump? Is it a molecular pump or what
It's
is
not
it?
a pump, but it can transfer the auxin.
Okay, but
But
it's a
it's not a pump.
So it's like a valve, a unidirectional valve.
It's unidirectional,
Okay.
very much, yes. Also, another developmental decision-making sensitive to mechanical cues is a weight or bending induction of a secondary growth, which is a thickening of the stem. Young stem look like this. It's a part of it. You see the vascular bundles. You see the edges of the tissue. You see a lot of ground cells filling up. Yeah, the stem is like that, and then these are just a section of it. And but this young tissue, when they undergo proper development and increase in the size and weight, what happens is they activate this stem cell population between, inside of a vascular bundle, and then they start to extend that in between to create the ring by de-differentiating the cells in between. As far as I know, this is the only event in animal or plant that involves, naturally involves de-differentiation of the stems, cells that has been differentiated into something else before. And then what happens is this ring of a meristem, particular type of a meristem called a cambium, they start to make new vascular tissues such as xylems, and the secondary xylems that's generated from this stem cell is commonly called wood. And wood is particularly mechanically supportive. So that happens especially at the bottom of the stem to support the stem to while they become much bigger and heavier. And that involves, again, the auxin accumulation at the bottom of the stem, and that is inducing stem cell activity in this the cambium stem cell. So my group is very much interested in this phenomena, and but I'm not going to talk a lot about it today. We are still in a lot of setting up phase. So, but previously I was looking at PIN1, PIN protein, and its response to tissue mechanical changes at the shoot apex. First, I like osmotic experiments, so I put them into osmotic expansion or osmotic shrinkage treatment. And what I observed was PIN basically disappeared away when the tissue lost the internal pressure and shrunk. Whereas when the cells expanded, the amount of pin per cell increased, but also those pins seems to be better plasma membrane localized. And so, also the pin polarity, when I look at it as a heat map within each cell, so individual cells, I divided the density of a pin 1 in one most sort of each sort of cell face divided by the least dense, cell face density. And basically, the more warm color you see, the more polarity you are seeing. And this is before treatment. After, the isosmotic doesn't change the polarity, but both messing with the shrinkage or expansion cause loss, decrease in the polarity of the yes.
Called polarity here is asymmetry in the
Yes,
distribution of
asymmetry.
fluorescence.
Yes.
Okay.
Yes.
Uh-huh.
So osmotic treatment induces so many different biological responses. So I try to see if it's a mechanical effect or something else by doing independent experimentation that induces a similar kind of changes, like more mechanical stress or strain and so forth. So centrifugation, pressing, artificial growth induction. Basically, in general, I got the same results. The more stress and or strain, the more pin 1 in its functional domain, which is the plasma membrane.
So now I get confused because you said that if you do osmotic treatment, so then I would say you increase the strain, right? Because you're shrinking or expanding the cells.
Yes.
But then you get less polarity. But now here you say you get more polarity.
Not more polar.
They go more to the
Okay, so it's a positive strain versus negative strain.
Yes.
Yes. So in the expansion, I got more pin, but when I shrunk it, it just basically like most of the pin got lost.
Okay, that's okay. You get so for expansion you get more pin.
Yeah, and
it's
shrinkage.
It's not polar.
And it's not polar either, exactly.
Okay.
Yeah, and also when we lost that pin, that polarity also was weakened as well.
Yeah.
So it's confusing. Yeah. Yes. So then I looked at the dynamics of this effect, and especially the effect of membrane in general, because membranes are endocytosis, exocytosis. They tend to be very sensitive to the membrane tension and so forth. So when I monitor them, yes, that effect was very rapid within 5 minutes. Like this is as fast as I could get to the confocal. Yeah. Massive influx of a pin signal, membrane signal, and then after 30 minutes or so, pin kind of disappears away, even with the immunolocalization, so they seems to be degraded. But then I do the reversible treatment, and then they come back to normal level or even more with a hyposmotic treatment within 30 minutes. So that was pretty dynamic effect, both on pin and membrane, and a pin seems to be particularly sensitive to this treatment compared to other plasma membrane proteins or plasma membrane itself, but it's a general effect. So from here, so my conclusion was, okay, pin plasma membrane localization is sensitive to mechanical stress or strain. From there, another team led by Marcus Heisler did fantastic, beautiful ablation studies, laser ablation studies to modify the direction of a mechanical stress in a very predictive manner. So by ablating cells like here, before the stress was isotropic, and then by ablating some cells here, you are introducing circumferential directionality to mechanical stress field. And what happened was the pin basically gets relocalized to the side away from the ablation side, and so similar kind of reorganization was talked about by Ruth very nicely 2 days ago. But yeah, so if you look at the cortical microtubule, which respond to mechanical stress too, that there's a quite nice correlations and so forth. And then since then, they seems to have a couple of more new data to suggest that the pin does localize to the side of the cell which is contains the most mechanical stress. So, well, that makes my life a bit difficult because before I thought it was all about mechanical strain, yeah, which is easier to sense if you think about the non-mechano-sensing factors like calcium channels and so forth. They tend to, experience a deformation and then induce that response. And even the membrane tension idea of a regulation of endocytosis, exocytosis is about mechanical, deformation. So that seems like cells sense mechanical stress independent of strain because they did the experiments to uncouple those two things, right? So this is one of the big questions that we have in our field, always hanging. How do cells sense mechanical stress independent of strain? If you have any good suggestions and so forth, please let us know. But I do want to study this kind of questions more, and the more I thought about it, working on tissue level alone is not entirely convincing because there are so many cues, so many chemical cues within the tissues. We kind of have to isolate the cells and then do the mechanical treatment and then have to see if that's sufficient or not. And so upon starting my own group, I started to establish a single cell system, culturing system combined with microfluidics to study how, for example, when cells get compressed, what kind of a response, like what kind of changes, physical changes are happening to the cell, and then that triggers what kind of a molecular response and so forth. For example, I'm very interested in cytoplasmic clouding effect when cells shrink. Maybe that's a very potent regulator of chemical activity. So, so I've been developing. My very talented grad student has been developing a microfluidic system to induce apply mechanical treatment as well as chemical treatment of cell biological drugs and so forth with microfluidics. And then here I would like to show you. Is it? Yeah. Well, now we have a system to, for example, hold the plant cells quite happily over a really long time to observe their response under the microscope. But also, combined with that, we are developing inducible stem cell differentiation system with the plant cells in which we extract leaf cells. We digest the cell walls away, take out just the inside of the cytoplasmic and the plasma membrane aspect of it, and then by culturing them as a single cells, they degenerate the cell wall, and for a while they stay as a single cells, with which we can do a lot of characterizations. But actually this protocol we are following is fantastic because they have shown that they can actually go back to almost totipotent phase and then become the entire plant subsequently from this after going through this kind of a system. So we are excited about the prospect of understanding cell dedifferentiation, stem cell activity, redifferentiation, and so forth with this system. Yes, and then those are the sort of fragments of what we are trying to do to understand how well plant structures sort of maintain their structural stability through the developmental modifications and so on. But we really need to understand that better at the more like macro scale, what's happening and how good that how robust that stabilization effect is. To do that, we should make digital plants basically, and with real information about geometry, also cell wall, material properties, and all sorts of things, and then to make it real plants, it has to be adaptive, yeah, because they change material properties, anatomy, geometry. So that makes our life a bit difficult. So with my collaborator in School of Informatics in Edinburgh, we are developing a platform to somehow make adaptive structural model, which has two parallel sort of components. First is FEM-based mechanical simulation, which is connected to developmental pattern formation modeling. And we calculate the, for example, mechanical stress, like pressure distribution in given geometry, given material properties, and so forth with FEM. And then we feed in that mechanical signal information into the developmental patterning program to go back and forth. That's sort of the idea. However, yeah, going back and forth basically. But we are facing a difficulty because for FEM, it's really important to have a realistic geometry. The little geometrical features seems to affect a lot in FEM modeling, whereas for developmental modeling, it's all abstractions. So we have to find sort of the right balance of how much we can abstract versus true to be, truth, the reality. Yes. But we are capturing 3D geometry as accurately as possible using a CT scan, for example, or we are trying a structure right or multi-photo 3D scanning, but this seems to be a bit too noisy. So also we are measuring actual tissue, living tissue material properties by doing tensile and bending characterizations. And we are a little bit proud of this sort of hold which keeps a stem like as happily as possible while they get tortured with all sorts of things. Okay, so that's sort of where we are. A lot of sort of setting up to really do start to answer questions and so forth. But before I finish, I would like to mention a little bit of how our studies sort of have importance in agriculture, actually. Have you seen something like this in the wheat or barley field? They fall, and then they kind of have domino effect, and they fall and they make a patch of, like fallen plants. It's called lodging. And once this happens, farmers have to give up on this entire patch. Sometimes it could be half of a field. Every couple of years, 20 to 70% of yield is lost due to this problem. Once they are like this, they get wet, and then the grain quality goes down, so it's no good. It's hard to harvest as well, apparently. And so this used to be much, much worse problem, actually, and it was one of the biggest targets of Green Revolution. They made the dwarf plants, stiffer plants, to avoid this problem, yeah? And it's still a problem, actually. And so, using plants' capability to adjust themselves according to mechanical stimulation, people in Asia has, actually had a very simple treatment they do with wheat and then barley at least, and sometimes with the rice. But they basically press on young wheat or barley plants, and that. Well, it used to be villagers line up and they step on them, but now, of course, they use the roller, and the effect is apparently quite, sort of clear, and it doesn't cost anything, and it's very ecologically friendly. No weird chemicals going into the soil or anything like that. So, but the molecular mechanism behind this effect has not been well understood, actually, at all. So my group is trying to tackle that problem too, and that's it. So first of all, I talked a lot about my postdoc works, which I did in Bern, Switzerland, and Lyon, France. So here are the people who were partners in crime with me, and fantastic collaborators all in all. And then right now I have these fantastic people that I'm collaborating with. And thank you very much for your attention. But yeah, by the way, so I have 3 sort of questions that are based about my research or related field in general that I would love to pick your brains with, if you could help. That would be great. Thank you.
Thank you a lot. Any questions? Any further questions?
Do you already have some results in single cell response? Do you know about the exocytosis and endocytosis?
So by compressing
Right.
or compressing
Yeah.
well. So that's where we are we're trying. It seems to be endocytosis, gets induced by compression, but it's really preliminary, and I don't want to. Yes, actually, you can observe with at the tissue level too. If you compress on the tissue, there's like massive influx of the pin and membrane in general. People thought that was a problem in general, but that's
Very interesting. Yeah.
yes, yeah.
Was there another question?
There are 2. Yes.
Take that one first.
Okay. Yes.
It's just not a complete answer, but for your second question up here, there are people who are working on developing the engineering theory for modeling growing structures,
That's
changing
fantastic.
material properties, the
That
complex
would be-
geometry.
that would be great.
The original thing was this paper by Rodriguez and Hoger and McCullough, but that's it. There are people building on it for continuous deposition of
Yes,
elements.
that
They're mostly
would be
thinking about
really
animal
great.
tissues, but it's not
Yes,
terribly
yeah,
different.
no, that would be fantastic. Yeah, yes, I would like to write down. Yeah, that would be great. And
I hope it doesn't sound silly, but how do you form the bonsai?
oh, bonsai. So, yeah, people think bonsai is all about cutting the right buds, huh? But actually, a lot of people think, okay, 2 things. First of all, to make a proper bonsai, you apparently have to choose very shallow pots and then tangle up like really strain, gives the physical constraint to the root growth. So that would keep them tiny. Yeah. But also the constant touching of the shoot. I think that has a
studied mechanically?
I don't know about that. I talked with, but I myself probably should start bonsai. Yeah,
You should start.
yeah, I should start.
Actually, I have a question to you. Because you asked, how can cells sense mechanical stress independent of strain?
Yes.
So whenever you draw such a stress-strain curve,
Yeah.
it basically implies if you change stress, you also change strain. So
Exactly.
how firm is the database for believing that these cells can sense stress independent of strain?
So that's there are particular parts of the plants. Yeah, if you would remember Belu's talk, that's uncoupled. Oops, sorry. Yeah, oh no. So tiny sort of graph, but with meristem like this is organ, this is meristem dome. Around here, actually here, there's a stronger compression, and then the cells still grow in that direction. So that must wait. No, I think I should look at this area. Sorry. So this area has a very sort of predictable ways by which they divide. They divide it this way, and then they expand first that way, and then they divide it this way. So there's a nice file of the cells and like this. So the strong mechanical stress field is this way, but the expansion is that way. And then the pin polarity or cortical microtubule alignment is all the way to do with this one. Overall, there are some domains in which you can sort of decouple them, partially at least, and then that always correlates better with mechanical stress direction than the strain. And that's how we are saying And maybe you can give us a bit more sort of insights into it, various, but still, we always wonder how that's possible. To be honest with you, how can cell sense stress without?
One thing which comes to my mind concerning this question, I don't know if it's relevant, is the growth of the stress fibers when they detect stress. When there's also, I mean, that might not be relevant for plant cells, right? But animal cells, when they detect stress, they strengthen the stress fibers to counteract the stress, so that there might not be much strain then, and you have an effect of the stress inside the cell. So I don't know if that is of any relevance.
But you'd expect you need some kind of deformation in order to feel.
Yeah, but that
right?
deformation is very small, right? You
Small,
just
yeah.
need to change the conformation of a protein a little.
Yeah.
Super sense.
One thing that I can add is that when you look at that curve, a very complex, very composite material is taken into account to drive that curve. But there are many, many components. I mean, the matrix, the fibers, cross-linkers, and the density of the fibers, all of these matters. So there must be a relation between the stress sensing, but stress where? I mean, when you are talking about the stress, it can be sensed in matrix, or the fiber network, or some other component. So the real thing that is happening there might not have anything to do with the curve that we are looking at. That is an outcome of these composite materials.
Another aspect that comes to mind, if you look at shapes in intact plants, that shape is also historically dominated. It's maybe the alignment of the fibers originated during the path of the cell towards that place.
From here and then.
So the single cell experiment would be extremely important to prove that it's really stress sensing and not some kind of memory.
Yes, that I agree with you halfway, and the other half is actually this cortical microtubule orientation is very dynamic, and that's actually only reporting as it's happening now, and yes, and so that's actually quite how to say, there's a history element sort of erased. So but I agree with it. I think a single cell tells us a lot.
For instance, we have been thinking about this mechanism a lot, but we have been thinking of the stress sensing as a strain density sensing in the fiber network. And if you assume that there are many, many fibers in one direction, and you connect the density of a strain to this stress sensing, that's one suggestion. But
So do you think that the cellulose polymerization could be affected by the amount of stress? I mean, because that is really a process where you need this kind of moving enzyme. That so if there's more resistance, you could maybe change, and that would change the microtubule organization and
the problem is that there is almost no
yeah,
experimental data.
no, it needs to know, but that
just a speculation.
that could be potential mechanism maybe.
Okay, so remaining discussion, we might shift to the tea break. We need to have our
Thank you.